Okay, we're going to do atmosphere, teach yourself, with me, Mr. Harris, sponsored by Tim Hortons Coffee, quality coffee at high street prices. Good on you. Right, we're going to start with the Earth's atmosphere and just a summary of what the atmosphere is, really. So if we drew a pie chart of the atmosphere, and we'll imagine this is dry, unpolluted air, then most of the atmosphere we'd see is, let's go here, most of the atmosphere would see more than 3/4, 78% is nitrogen gas. Fairly inert gas. We'll talk about it more in topic 15 when we talk about the Haber process, but for most of our reactions, interactions, we don't do much nitrogen chemistry. We don't have much any chemistry reactions with nitrogen. Most of the rest, 21%, is oxygen, of course, the gas that we need to breathe, and we need that percentage to be fairly high. If it goes down, then we start to struggle when you climb mountains and so on. That leaves a very thin sliver, about 1%. Most of that 1%, nearly 1% actually, is argon. Is nearly 1% of that, and then there's other gases from group 0, helium, neon, krypton, xenon, radon would all be in there, the other group 0 gases. And carbon dioxide is really a very, very tiny amount of that. It's about 0.04% of that that sliver is carbon dioxide. We'll obviously talk about carbon dioxide in more detail when we talk about global warming, but people are often surprised to see that carbon dioxide is such a small percentage of the atmosphere, especially since it gets talked about a lot in the news and the media, and the huge amounts of carbon dioxide that we're releasing because we're burning fossil fuels. But actually, carbon dioxide is a very tiny amount of the air, and all plant life, every plant on the planet is drawing from that small amount of carbon dioxide. Okay, so that's the percentage composition of unpolluted dry air on planet Earth today. So how did it get to be there? Because if we went back 4.5 billion years ago, around about the time the Earth was being formed, the composition of the atmosphere was very different. The atmosphere consisted of, and I'm not going to draw a pie chart because we don't really know the exact compositions, but we know that the atmosphere contained an awful lot of carbon dioxide. That might have been the most common gas on the planet. Probably contained an awful lot of water vapor because the Earth was still pretty hot at the beginning when it was formed. So most of the water on the planet that we have now would have been in the vapor state. There would have been some methane, ammonia. Formula for these, methane is CH4, ammonia NH3, and maybe a few other gases as well, hydrogen sulfide, sulfur dioxide. Would have been a pretty toxic mixture, certainly not one that we could have survived on. But most importantly, we don't see any oxygen. There was no oxygen in the early Earth. So where did the oxygen come from? Well, the two important changes that we can focus in on here is the fact that the oxygen has appeared from, well, not from out of nowhere, obviously from life, and the carbon dioxide that made up a majority of the atmosphere 4.5 billion years ago has largely gone, whittled down to a tiny, slim percentage there. So this is generally due to plant life, and the amazing process of photosynthesis. So plants would have started off 2.5, 3, maybe as much as 3.5 billion years ago as very simple single-celled bacteria, the simplest form of life, and photosynthesizing. They take the water and the carbon dioxide from the atmosphere around them and transform it. So they take water and carbon dioxide and transform that into glucose, which of course can be used by the plants to store and to release energy, and oxygen gas. And if we 6 symbols in there, glucose, C6H12O6 plus oxygen, and then we need some 6s, 1, 2, 3, to balance the equation. So plant life photosynthesizing over billions of years slowly transformed our atmosphere, using up that huge amount of carbon dioxide and obviously some of the water, and making oxygen. And that would have been a very slow process. Initially, in fact, some of the oxygen that was released would have just gone into the oceans and would have reacted with various metals in the ocean, like iron, would have made iron oxide, and that would have taken hundreds of millions of years, and then eventually all the iron and the other minerals in the ocean were used up, and so some of that oxygen slowly started to filter into the atmosphere itself. And once there, it gets transformed into the ozone layer, which is a layer of sort of special oxygen, O3, around the Earth, around the stratosphere, which protected us from harmful UV rays and then allowed more complicated life to form and roam around on the planet. And of course, animals use that oxygen in order to release energy and move around and do all the exciting things that we do that plants can't. Okay, so we've just got a couple of other things. The water vapor would have turned into oceans. The Earth's cooled down and condensed, so that's gone. Things like ammonia would have reacted with hot rocks and formed some of the nitrogen there. Methane would have slowly reacted and formed carbon dioxide, which would have then got used up. Slowly the carbon dioxide was used up. I'll just talk about locked-in carbon. So locked-in carbon is the idea that the carbon dioxide is being used to make plants. So the plants are physically building themselves out of carbon, which they've extracted from the atmosphere in the form of carbon dioxide. And when they die, well, most things when they die, they get broken down by bacteria, and the bacteria release that carbon back into the atmosphere. We turn back into carbon dioxide. But in certain special situations where there's no air around, like at the bottom of swamps or maybe at the very bottom of the ocean, things wouldn't be able to break down. So we can imagine lots of sea creatures over millions of years forming in their bodies, their shells, the hard shells, sinking to the bottom of the ocean and forming layers and layers of carbon. So we could sort of picture the bottom of the ocean here, and then layer upon layer upon layer of shells of creatures here, forming. That was supposed to be a fish. It wasn't very good, was it? No fish. Forming and getting trapped by more layers of carbon, and then eventually by over time and because of the compression, that carbon then gets locked in and forms carbon rock or minerals. It's basically rock. For example, calcium carbonate. That's the rock that forms marble and limestone and chalk, which contains carbon. That carbon comes originally from sea creatures. Also things like coal and other fossil fuels, which are very rich in carbon. That's why we use them as fuels. They burn really, really well. And so that carbon has then been sort of locked in, trapped under the Earth's crust for millions of years until we've come along and discovered it and dug it up. So that's the term locked in carbon. So a lot of that carbon dioxide that used to be in the atmosphere has now turned into rock or coal or oil and so on, and is part of the structure of the Earth.